Project Orion was a study of a spacecraft intended to be directly propelled by a series of explosions of atomic bombs behind the craft. Early versions of this vehicle were proposed to take off from the ground with significant associated nuclear fallout. Later versions were presented for use only in space. The idea of rocket propulsion by combustion of explosive substance was first proposed by Russian explosives expert Nikolai Kovalchich in 1881, and in 1891 similar ideas were developed independently by German engineer Hermann Ganswind. General proposals of nuclear propulsion were first made by Stanislaw Ulam in 1946, and preliminary calculations were made by F. Rain and Ulam in a Los Alamos memorandum dated 1947. The actual project, initiated in 1958, was led by Ted Taylor at General Atomics and physicist Freeman Dyson, who at Taylor's request took a year away from the Institute for Advanced Study in Princeton to work on the project. The Orion concept offered high thrust and high specific impulse, or propellant efficiency, at the same time. The unprecedented extreme power requirements for doing so would be met by nuclear explosions of such power relative to the vehicle's mass as to be survived only by using external detonations without attempting to contain them in internal structures. As a qualitative comparison, traditional chemical rockets, such as the Saturn V that took the Apollo program to the Moon, produce high thrust with low specific impulse, whereas electric iron engines produce a small amount of thrust very efficiently. Orion would have offered performance greater than the most advanced conventional or nuclear rocket engines then under consideration. Supporters of Project Orion felt that it had potential for cheap interplanetary travel, but it lost political approval over concerns with fallout from its propulsion. The Partial Test Ban Treaty of 1963 is generally acknowledged to have ended the project. However, from Project Longshot to Project Daedalus, Mini-Mag Orion, and other proposals which reach engineering analysis at the level of considering thermal power dissipation, the principle of external nuclear pulse propulsion to maximize survivable power has remained common among serious concepts for interstellar flight, without external power beaming and for very high-performance interplanetary flight. Such later proposals have tended to modify the basic principle by envisioning equipment driving detonation of much smaller fission or fusion pellets, although in contrast Project Orion's larger nuclear pulse units were based on less speculative technology. Basic principles. The Orion nuclear pulse drive combines a very high exhaust velocity, from 19 to 31 km per second in typical interplanetary designs, with meganewtons of thrust. Many spacecraft propulsion drives can achieve one of these or the other, but nuclear pulse rockets are the only proposed technology that could potentially meet the extreme power requirements to deliver both at once. Specific impulse measures how much thrust can be derived from a given mass of fuel, and is a standard figure of merit for rocketry. For any rocket propulsion, since the kinetic energy of exhaust goes up with velocity squared, whereas the momentum and thrust goes up with velocity linearly. Obtaining a particular level of thrust requires far more power each time that exhaust velocity and specific impulse is much increased in a design. Goal. The Orion concept detonates nuclear explosions externally at a rate of power release which is beyond what nuclear reactors could survive internally, with known materials and design. Since weight is no limitation, an Orion craft can be extremely robust. An unmanned craft could tolerate very large accelerations, perhaps 100 grams. A human crewed Orion, however, must use some sort of damping system behind the pusher plate to smooth the instantaneous acceleration to a level that humans can comfortably withstand, typically about 2 to 4 grams. The high performance depends on the high exhaust velocity. In order to maximize the rocket's force for a given mass of propellant, the velocity of the plasma debris is proportional to the square root of the change in the temperature of the nuclear fireball. Since fireballs routinely achieve 10 million degrees Celsius or more in less than a millisecond, they create very high velocities. However, a practical design must also limit the destructive radius of the fireball. The diameter of the nuclear fireball is proportional to the square root of the bomb's explosive yield. The shape of the bomb's reaction mass is critical to efficiency. The original project designed bombs with a reaction mass made of tungsten. The bomb's geometry and materials focus the X-rays and plasma from the core of nuclear explosive to hit the reaction mass. In effect, each bomb would be a nuclear-shaped charge. A bomb with a cylinder of reaction mass expands into a flat, disc-shaped wave of plasma when it explodes. A bomb with a disc-shaped reaction mass expands into a far more efficient cigar-shaped wave of plasma debris. The cigar shape focuses much of the plasma to impinge onto the pusher plate. The maximum effective specific impulse (ISP) of an Orion nuclear pulse drive generally is equal to, where CO is the collimation factor, VE is the nuclear pulse unit plasma debris velocity, and GN is the standard acceleration of gravity. A collimation factor of nearly 0.5 can be achieved by matching the diameter of the pusher plate to the diameter of the nuclear fireball created by the explosion of a nuclear pulse unit. The smaller the bomb, the smaller each impulse will be, so the higher the rate of impulses and more than will be needed to achieve orbit. Smaller impulses also mean less G-shock on the pusher plate and less need for damping to smooth out the acceleration. The optimal Orion drive bomblet yield was calculated to be in the region of 0.15 knots, with approx 800 bombs needed to orbit and a bomb rate of approx 1 per second. Sizes of Orion vehicles. The following can be found in George Dyson's book. The figures for the comparison with Saturn V are taken from this section and converted from metric to US short tons. In late 1958 to early 1959, it was realized that the smallest practical vehicle would be determined by the smallest achievable bomb yield. The use of 0.03 knots bombs would give vehicle mass of 880 tons. However, this was regarded as too small for anything other than an orbital test vehicle, and the team soon focused on a 4,000-ton base design. At that time, the details of small bomb designs were shrouded in secrecy. Many Orion design reports had all details of bombs removed before release. Contrast the above details with the 1959 report by General Atomics, which explored the parameters of 3 different sizes of hypothetical Orion spacecraft. The biggest design above is the Super Orion design, at 8 million tons. It could easily be a city. In interviews, the designers contemplated the large ship as a possible interstellar ark. This extreme design could be built with materials and techniques that could be obtained in 1958 or were anticipated to be available shortly after. The practical upper limit is likely to be higher with modern materials. Most of the 3,000 tons of each of the Super Orion's propulsion units would be inert materials such as polyethylene or boron salts, used to transmit the force of the propulsion unit's detonation to the Orion's pusher plate, and absorb neutrons to minimize fallout. One design proposed by Freeman Dyson for the Super Orion called for the pusher plate to be composed primarily of uranium or a transuranic element, so that upon reaching a nearby star system the plate could be converted to nuclear fuel. Interplanetary applications. The Orion nuclear pulse rocket design has extremely high performance. Orion nuclear pulse rockets using nuclear-efficient type pulse units were originally intended for use on interplanetary spaceflights. Missions that were designed for an Orion vehicle in the original project included single stage to Mars and back, and a trip to one of the moons of Saturn. One possible modern mission for this near-term technology would be to deflect an asteroid that could collide with Earth. The extremely high performance would permit even a late launch to succeed, and the vehicle could effectively transfer a large amount of kinetic energy to the asteroid by simple impact. Also, such an unmanned mission would eliminate the need for shock absorbers, the most problematic issue of the design. Nuclear-fission pulse unit-powered Orions could provide fast and economical interplanetary transportation with useful human crewed payloads of several thousand tons. Interstellar missions. His 1968 paper, Interstellar Transport, retained the concept of large nuclear explosions, but Dyson moved away from the use of fission bombs and considered the use of 1 megaton deuterium fusion explosions instead. His conclusions were simple. The debris velocity of fusion explosions was probably in the 3,000 to 30,000 km per second range, and the reflecting geometry of Orion's hemispherical pusher plate would reduce that range to 750 to 15,000 km per second. To estimate the upper and lower limits of what could be done using contemporary technology, Dyson considered two Starship designs. The more conservative energy-limited pusher plate design simply had to absorb all the thermal energy of each impinging explosion without melting. Dyson estimated that if the exposed surface consisted of copper with a thickness of 1 mm, then the diameter and mass of the hemispherical pusher plate would have to be 20 km and 5 million metric tons, respectively. 100 seconds would be required to allow the copper to radiatively cool before the next explosion. It would then take on the order of 1,000 years for the energy-limited heat-sink Orion design to reach Alpha Centauri. In order to improve on this performance while reducing size and cost, Dyson also considered an alternative momentum-limited pusher plate design where an ablation coating of the exposed surface is substituted to get rid of the excess heat. The limitation is then set by the capacity of shock absorbers to transfer momentum from the impulsively accelerated pusher plate to the smoothly accelerated vehicle. Dyson calculated that the properties of available materials limited the velocity transferred by each explosion to 30 meters per second independent of the size and nature of the explosion. If the vehicle is to be accelerated at 1 Earth gravity with this velocity transfer, then the pulse rate is 1 explosion every 3 seconds. The dimensions and performance of Dyson's vehicles are given in the table below. Later studies indicate that the top cruise velocity that can theoretically be achieved by a tellur-ulam thermonuclear unit-powered Orion Starship, assuming no fuel is saved for slowing back down, is about 8% to 10% of the speed of light. An atomic Orion can achieve perhaps 3% to 5% of the speed of light. A nuclear pulse drive starship powered by fusion antimatter catalyzed nuclear pulse propulsion units would be similarly in the 10% range, and pure matter antimatter annihilation rockets would be theoretically capable of obtaining a velocity between 50% to 80% of the speed of light, in each case saving fuel for slowing down halves the max speed. The concept of using a magnetic sail to decelerate the spacecraft as it approaches its destination has been discussed as an alternative to using propellant. This would allow the ship to travel near the maximum theoretical velocity. At 0.1 c, Orion thermonuclear starships would require a flight time of at least 44 years to reach Alpha Centauri, not counting time needed to reach that speed. At 0.1 c, an Orion starship would require 100 years to travel 10 light-years. The astronomer Carl Sagan suggested that this would be an excellent use for current stockpiles of nuclear weapons. Later developments. A concept similar to Orion was designed by the British Interplanetary Society in the years 1973–1974. Project Daedalus was to be a robotic interstellar probe to Barnard's star that would travel at 12% of the speed of light. In 1989, a similar concept was studied by the U.S. Navy and NASA in Project Longshot. Both of these concepts require significant advances in fusion technology, and therefore cannot be built at present, unlike Orion. From 1998 to the present, the Nuclear Engineering Department at Pennsylvania State University has been developing two improved versions of Project Orion known as Project ICAN and Project AIM-STAR using compact antimatter catalyzed nuclear pulse propulsion units, rather than the large inertial confinement fusion ignition systems proposed in Project Daedalus and Longshot. Economics. The expense of the fissionable materials required was thought to be high, until the physicist Ted Taylor showed that with the right designs for explosives, the amount of fissionables used on launch was close to constant for every size of Orion from 2,000 tons to 8 million tons. The larger bombs used more explosives to supercompress the fissionables, increasing efficiency. The extra debris from the explosives also serves as additional propulsion mass. The bulk of costs for historical nuclear defense programs have been for delivery and support systems, rather than for production cost of the bombs directly. After initial infrastructure development and investment, the marginal cost of additional nuclear bombs in mass production can be relatively low. In the 1980s, some U.S. thermonuclear warheads had $1.1 million estimated cost each. For the perhaps simpler fission pulse units to be used by one Orion design, a 1964 source estimated a cost of $40,000 or less each in mass production, which would be up to approximately $0.3 million each in modern-day dollars adjusted for inflation. Project Daedalus later proposed fusion explosives detonated by electron beam inertial confinement. This is the same principle behind inertial confinement fusion. Theoretically, it could be scaled down to far smaller explosions, and require small shock absorbers.